Welcome to the second lesson in All Biology's Chemistry. This lesson is about compounds and chemical bonding. In this lesson, the objectives are going to be that you will be able to define a compound, explain why elements combine to form compounds, define the term chemical bond, compare and contrast ionic and covalent bonds, and understand why ionic and covalent bonds form. Finally, we will be able to predict which type of bond will likely form when given two or more elements. So, as you've already learned, compounds are substances that contain atoms of two or more elements that are chemically combined in fixed proportions. Please make sure that you have those three parts of the definition firmly in your notes and firmly in your understanding, that it involves two or more elements, that they're chemically combined, and that they have to be combined in fixed proportions. So when two atoms meet, how do they form a compound? Well, the individual subatomic particles either attract or repel one another, and we've talked about this a little bit in class. Electrons repel each other. The nuclei repel each other. But electrons and the nucleus are attracted to each other. So there's this tension here between particles that have similar charges repelling and particles with different charges attracting. The repulsions that exist are going to increase the kinetic energy of particles. It's going to force them to move away. Whereas the attractions are going to decrease the kinetic energy of particles. It's going to make them come together and fit together. Atoms like to find arrangements that minimize the kinetic energy of their particles. They want to minimize the repulsion. So why combine? Compounds form because atoms prefer to have a valence energy level that is filled with electrons. Well, what is a valence level? A valence level is the outermost energy level of an atom. Here on our carbon atom, you can see the valence level has 4 electrons in it. A partially filled level is not as stable as one that's full. A partially filled outermost energy level usually achieves minimization of that energy, of kinetic energy of repulsion, by making the atom stable electrically by bonding with other atoms. Does this carbon atom have a filled valence energy level? No. The second level, as we've learned, holds 8 electrons, and the carbon atom only has 4. It can basically fill its level if it has 4 more electrons. So how do I achieve this stability? Well, it can meet one of 2 criteria, it turns out. First, as we just said, an atom can fill its valence energy level with the maximum amount of electrons that one can hold. For the first energy level, that's 2. For the second energy level, that's 8. For the third energy level, that's 18, and so on. Or they can fill their valence energy level with 8 electrons, provided that the level can hold 8. So for any level above 2, for 2 and above, this rule would apply. So this is often referred to as the octet rule. And for reasons that I haven't explained to every student yet, the number of 8 fills a certain type of orbitals in that valence level that seems to form a nice minimization of kinetic energy for the electrons that are traveling in those particular orbitals. So when atoms come into proximity to one another, their electrons are going to repel one another, and no bonds form, unless I slam them together. Atoms are moving at sufficient speed. They have kinetic energy. And the first law of thermodynamics states that energy can't be created nor destroyed, but it can be converted from one form into another. So if an atom is moving and having kinetic energy of motion, when it slams into another atom, some of that kinetic energy could be stored in the electrons of those atoms, bonding them together so the energy is just transferred, not destroyed. So, in short, bonds form when the kinetic energy of colliding atoms overcomes their initial repulsion, and any resulting forces of attraction are greater than any remaining forces of repulsion. So if 2 atoms slam together, and by bonding, they can achieve that octet rule or fill their valence energy levels in some way, or get closer to that goal, that might be a reason for staying in that arrangement rather than bouncing off one another and going in separate ways. And that seems to be the case for many atoms. So, kinetic energy can be lost as heat or light, or it can be stored in a chemical bond. And that second is what we're going to be talking about here in this particular tutorial. Chemical bonds are the attractions that hold two or more atoms together to form a compound. When bonds form, energy is stored. And when bonds are broken, energy is released. It's important to note that a chemical bond represents stored chemical energy. It's a very important thing to remember. So there are two ways that atoms can do this. Actually, there are many types of attractions between atoms, but the two most significant and strongest of bonds are ionic bonds and covalent bonds. Let's take a look at ionic bonds first. So here is a picture of a sodium atom and a chlorine atom. And these Bohr models are drawn. The electrons are spread out on these atoms, but you learned that they are actually paired up in certain ways. Take a minute to maybe pause the video and jot these two atoms down in the spot on your notes or somewhere where you can manipulate them, and come back when you have got that done. So you'll notice that if you count the electrons, the sodium atom has 11 and the chlorine atom has 17. These are both neutral atoms because the number of electrons equals the number of protons for each atom. But if I move an electron from sodium to chlorine, you can see that that changes things. All right? Why would this happen? Well, that one electron in the outermost or valence energy level of sodium is all by itself. If sodium were to give up that electron, it now would have a full valence energy level. The second level is full, and since there are no electrons in the third level, it essentially goes away. So the second level becomes the valence level, and it's full, and sodium is stable and happy. Chlorine has 7 electrons in its outermost energy level, and if it got one more, it would have 8. And by the octet rule, chlorine would have a stable valence energy level. And so when sodium and chlorine collide together with enough energy, this is exactly what happens. Now notice that sodium and chlorine are no longer neutral atoms. Sodium has lost an electron. It has 11 protons and 10 electrons. Therefore, it now has a charge of +1 because it has one more proton than electron. Chlorine has a negative charge now. It has 17 protons but 18 electrons. It has one more electron than protons, and so therefore it is a negative ion. The atoms are no longer electrically neutral in this position, and so when this happens, they each have equal and opposite charges, as we've just learned. And because of the equal and opposite charges, these two atoms are now going to attract. The two ions, as they're called when they have a charge, attract one another because the positive charge of the sodium ion is going to attract to the negative charge of the chlorine ion. And that's what's called an ionic bond. An atom with an electrical charge is called an ion, and as a result of their opposite charges, sodium ions and chlorine ions attract each other. An ionic bond is the chemical bond formed between ions with opposite charges. Because sodium has released an electron, it also has reduced its energy. Since chlorine has gained an electron, but it's put that in a stable arrangement with another electron in an orbital in its valence energy level, its kinetic energy has also been reduced. But that kinetic energy can't be lost. The law of thermodynamics says it has to go somewhere, and that goes into a bond. Well, what atoms are going to bond in this way? Well, it turns out that atoms that like to give up electrons are on the left side of the periodic table, and atoms that like to gain electrons are almost all the way to the right. So here in column 1, or group 1, all of these atoms are arranged in the periodic table because they only have one valence electron. And they would love to give that to these atoms over here in group 7. Because in group 7, where the large arrow is pointing down to fluorine, chlorine, bromine, iodine, and acetine, these atoms all have 7 valence electrons. So by getting one more, they would complete their octet rule. The elements in the second column in group 2 have 2 valence electrons. And if they were to give their 2 electrons to the elements in group 6, then group 6 would have a full valence energy level. So the atoms in these 2 columns often form ionic bonds. It's important to note that the atoms on the far right, with the exception of the column in red, which are noble gases and have a special chemistry, are more electronegative, meaning they like to take electrons and become negative ions. So to review, ionic bonds involve a transfer of electrons, and they result when ions of opposite charges attract one another. Let's go back to our 2 ways to bond, because there is another way. It's called a covalent bond. Let's talk about how this bond is different than an ionic bond. What happens when an atom has 4, 5, or even 6 valence electrons? It doesn't want to give them up, but it also needs quite a few, 4, 5, or 6, to become a stable atom. Atoms can also share electrons. They can share 1 or sometimes up to 3 pairs of electrons. When 2 atoms share electrons, the shared electrons occupy orbitals around both of the atoms. The electrons move so quickly that it's difficult to predict which atom they're orbiting at any given time. Therefore, both atoms have the experience of having both electrons in their valence energy levels. It's important to note that this type of arrangement only occurs with valence electrons. Electrons in lower energy levels do not share. Water is a wonderful model for covalent bonding. If you look at the hydrogen atom on the left, it has 1 proton, 0 neutrons, and 1 electron. The oxygen atom has 8 of each subatomic particle. So how many valence electrons does each have? Hydrogen has 1. Oxygen has 6. How many more electrons does each atom need to fill its outermost energy level? Hydrogen only has 1 energy level, so it can fill it with 2 electrons. It needs 1 more. Oxygen has 6 electrons in its outermost or valence energy level, and it needs 2 more to fill that level with 8. So how might each of these atoms fill its outermost energy level? Well, it turns out that 2 hydrogen atoms could each share their electron with oxygen and form the compound that you and I know as H2O. This is what it looks like. The blinking electrons here represent shared pairs of electrons. Each hydrogen is sharing a pair of electrons with oxygen. Oxygen is sharing an electron each with hydrogen. How many valence electrons does each atom have now? Well, when you determine that, you have to count the shared electrons in both atoms that are sharing them. So, for instance, hydrogen would have 2 electrons in its valence level. The other hydrogen would also have 2, and the oxygen atom would have 8. All of them have now managed to fill their valence energy level by sharing pairs of electrons. A covalent bond, then, is what is formed when this sharing occurs. Think of it as co, meaning together, valent as in valence energy levels. We're putting those 2 levels together to share 1 or more pairs of electrons. And the name for something that occurs when atoms combine and share electrons is called a molecule. And whereas an atom is to an element, a molecule is to a compound. It's the simplest part of a substance that retains all the properties of that substance. Strictly speaking, ionic bonds don't form molecules because ions are still free to move about quite readily in a solution or in a substance, even though they are closely associated with other ions. It is merely an attraction, not a physical arrangement of sharing electrons. Molecules are much stronger than ions. Representing this, you can see that we sometimes represent these molecules with chemical formulas. Sometimes we represent them with structural formulas, where each line between the atoms represents a shared pair of electrons. So you can see here that when hydrogen gas forms, two hydrogen atoms share a pair of electrons. When oxygen gas forms, each oxygen atom shares two electrons with the other, and thus they both can satisfy each other's valence energy level. In water, we've already learned that each hydrogen shares one pair of electrons with oxygen. Carbon has an outermost energy level that's partially filled, as we've learned. It only contains 4 electrons. And because of that, carbon can form up to 4 single covalent bonds. That makes carbon extraordinarily versatile for forming lots of different bonds with lots of different things. And that's why carbon is such an important, essential element for life. Any substance that contains carbon is referred to as an organic or carbon-containing compound. The only exceptions are carbon monoxide and carbon dioxide, which strictly speaking are not considered organic compounds. Finally, we'll wrap up with a comparison of these two types of bonds so you can have them separated in your mind. First, ionic bonds involve a transfer of electrons from one atom to another, whereas covalent bonds share electrons between two atoms. Ionic bonds usually occur when groups 1A and 2A elements bond with groups 6A or 7A elements. Remember the opposite sides of the periodic table. Covalent bonds usually occur between non-metal elements that have 3, 4, 5, or 6 valence electrons. Carbon, hydrogen, nitrogen, and oxygen often form covalent bonds. Are you beginning to see a relationship between the elements that form covalent bonds and the ones that are important to living things? Finally, covalent bonds are very, very strong. And ionic bonds also, but second to covalent bonds in their strength. Later on in the course, we'll talk about other types of bonds that form between atoms and also between molecules. None of those are as strong as ionic or covalent bonds. So I hope you've learned a little bit about bonding from this presentation and from reading your chapter. When you come in next to look at some modeling of these compounds, this information should be helpful to you when you do that. Have a great evening.